Okay, welcome back to the lecture on Fourier series, and in the last lecture we have discussed Fourier series representation of a function of period 2L in general, or we were talking about the functions of period 2 pi as well. So, if a function is periodic of period 2L, then its Fourier series will be given by a 0 by 2, and it is a constant which will depend on the function. So, here 0 1 to infinity a n cos n pi x over L plus b n sin n pi x over L, and where these coefficients. So, a n 1 over L minus L to L f x cos n pi x over L dx at k or this n here. So, n 0 1 2 and so on, and this b n 1 over L minus L to L f x sin n pi x over L dx, and this n was 1 2 and all. And then we have seen that if this function f x is piecewise continuous and one sided derivatives of f exist at each point in the domain, then we have this series equal to, so we have the f x plus the right limit of f at x and f x minus divided by 2, and this is equal to that series if the function is piecewise continuous and one sided derivatives exist and they are finite. So, then we have this series converges, and that the value of the series is equal to the average value of the function at that point. And we have also mentioned that at the point of continuity, since there we have f x plus is equal to f x and that is equal to f x minus 1. So, at the point of continuity this is simply f x. So, that series converges to the point to the functional value. So, now we continue with the more examples, and the first example I consider here, it is expand f x is equal to sin x in a Fourier series. So, now if we see this function, what we observe, so it is 0 to pi and so on. It is a modulus, so we do not have the negative part. So, now there are two possibilities to get this Fourier series of this problem, because we can see here that this pi, so is the period of the function, because it repeats the same value after this pi. So, we can work out in this interval 0 to pi and taking this pi as a period of this function, or the second possibility is as the standard case we take. So, we take here minus pi to pi interval and consider this 2 pi as its period, because we can take anyway this 2 pi also a period, because after that 2 pi also the function values the function repeats its values. So, what we do, these two possibilities we will consider and see, and definitely we will get the same series of course at the end. So, let us just, to make it more clear, let us just continue with the case 1. So, that means we work with the function. So, we treat this treat f x as a function of period pi, and we work in the interval and take the interval 0 to pi. And that is a good point to discuss, that we should not always I mean, it is not necessary to work with always with the symmetric interval minus pi to pi. So, we can also work with any interval. So, we take here 0 to pi, and then this f x, the general Fourier series, a 0 by 2 n 1 to infinity a n cos n pi x over L plus b n sin n pi x over L, and this was the series for a function of period 2L. So, a n as 1 over L minus L to L in general case, and cos n pi x over L dx, or we can take also 1 over L 0 to 2 pi, because it's a periodic function. So, we integrate in any range with length 2 pi or 2L, sorry 2L, it will be the same. So, f x cos n pi x over L and dx, or this b, and similarly we have 1 over L 0 to L 0 to 2L 0 to 2L and f x sin n pi x over L dx. So, in this case which we are considering now, our 2L is the period is taken in this form 2L, and that is pi. So, basically what we have, L is pi by 2. So, now we calculate a 0 first. So, this a 0 will be 1 over, and L is pi by 2. So, pi by 2, and we have 0 to 2L, that means pi, and f x dx. So, we have 2 over pi and 0 to pi, f x is sin x. So, 0 to pi, this mod sin x is positive. So, we have sin x dx, and that value is minus cos x, and 0 to pi. So, cos pi minus 1, and minus is there already. So, 1 and minus 1 will be again 2. So, we have 4 over pi, this value. Now, we calculate the a n. So, a n is 2 over pi again, the same 1 over L factor is there, and 0 to 2 pi will come with this function sin x and cos 2 n x dx. So, then we have 1 over pi, and this 2 sin x cos 2 n x we write in sin a plus b form, side 2 n plus 1 x sin a plus b, and then plus sin a minus b, but we will take b minus a. So, with sin we will get minus sin. So, sin 2 n minus 1 x and dx, we integrate now. So, we have sin x, that is cos, with minus sin 2 n plus 1 x over 2 n plus 1, and the limit 0 to pi, and we have here 2 n minus 1 x over 2 n minus 1, and again 0 to pi. So, we have 1 over pi, and then when we put this pi here, we get minus 1 over, keep minus 1 power 2 n plus 1. So, we have with minus and minus 2 n plus 1 over 2 n plus 1, and then minus minus plus, cos 0 would be 1. So, over 2 n plus 1. Similarly, here we have minus 1 2 n minus 1 over 2 n minus 1, and we have minus then 1 over 2 n minus 1. This we can simplify, and this after simplification, because this is 2 n plus 1. So, always a odd number here. So, we will get minus. So, we have here then plus, and similarly here this 2 n. So, n is 1, 2 and so on. So, here again we have always the odd numbers will get minus. So, minus 2 over 2 n minus 1, and here we will get 2 over 2 n plus 1, and then the further simplification. So, we will get minus 4 over pi and 4 n square minus 1 for n square minus 1. So, now we calculate b n. We have 2 over pi 0 to pi, and we have sin x and sin 2 n x dx. Again we take 1 over pi 0 to pi 2 sin x. So, sin a sin b, we have cos a minus b. So, cos or b minus a is the same. So, we write in this form 2 n minus 1 x and minus cos a plus b. So, 2 n plus 1 x, and then we have this dx. And now the integral will be the sin 2 n minus 1 x, and here also sin, and the sine function, when we take this x is equal to pi or we take 0, it will be 0. So, the value we will get 0. Then the Fourier series a naught by 2. So, a naught was 4 by pi. So, we have 2 over pi, and we have n 1 to infinity minus 4 over pi and 4 n square minus 1 cos 2 n x. So, this is 2 over pi minus 4 over pi and n from 1 to infinity cos 2 n x over 4 n square minus 1, and this x was 0 to pi. So, now we take the second approach, and in the second approach we have, so if we would have taken second possibility, that is the period is 2 pi. So, we take again minus pi to pi, the standard interval, and we will get here n is equal to pi. In this case again this f x is 0 by 2 1 to infinity, and we have this standard series in this interval. So, n x plus b n sin n x, and this a n is 1 over pi minus pi to pi f x cos n x dx, and b n is 1 over pi and minus pi to pi f x sin n x dx. Okay, let us just see first this b n, because this f x is a odd even function, and we have here the odd function. So, this was even function. We will come to this point in a minute more into the detail, and this is the odd function, because sin minus x is minus sin x, and here sin f minus x is f x. So, it is cos x, then the product will be anyway an odd function. So, the integrand is odd, and we are integrating over the symmetric interval minus pi to pi. So, this value will be 0 without further calculations. So, now this a is naught, we can calculate 1 over pi and minus pi to pi, and we have this f x dx. And in this case also, let me just simplify this, that this a n will be because it is a here even function, so the product is even. So, minus pi to pi will be 2 times 0 to pi, and we have this f x and cos n x dx. So, this is 2 over pi 0 to pi, and this is sin x only dx. So, this cos x, and then we have this value cos pi minus, and with the minus sign we will get again the 2 out of this integral. So, we will get 4 over pi, and then a n 2 over pi 0 to pi sin x cos n x dx, which we can integrate. So, I am writing directly these values, and these values will come for n 2 3 and so on. So, will be 1 over pi times the 0 if n is odd, and this will come 2 over n plus 1 minus 2 over n minus 1 when n is even, and this is true for 2 3 and so on. So, again for a1 we need to calculate, and that is 2 over pi 0 to pi sin x cos x dx. So, this 2 times sin x cos will be sin 2 x, then cos 2 x over 2. So, this will be again 0. So, what will be the Fourier series in this case? So, what we have here finally, this is 2n minus 2 and minus 2n minus 2. So, we have minus 4 over n square minus 1. So, if we write this Fourier series now, we have f x 2 over pi minus 4 over pi, and we have cos 2 x over 3 plus cos 4 x over 15 plus cos 6 x over 35 and so on. So, this Fourier series and the Fourier series we got by treating this function of period pi, they both are basically the same. It is just if we expand this. So, minus 4 over pi will come, and then we have n is equal to 1. So, cos 2 x over 3, then the second term we have n is equal to 2. So, 4 x over 16 minus 1 15 and so on. So, it is the same Fourier series what we get here. So, here what we have seen that we can work with any general integral, not always the symmetric interval. So, now we go for the another important point here, which partially we have discussed in this example, that the Fourier series for even and odd functions, for even and odd functions. So, again just to remind, a function is said to be even if we have f minus x is equal to f x for all x, and an odd function if we have f x is equal to minus f x for all x. So, in this case what will happen, just let us consider this Fourier series a naught by 2 n 1 to infinity a n cos n x plus b n sin n x with the standard in period 2 pi, and then we have this a n 1 over pi minus pi to pi f x cos n x dx. And now what will happen here, because we have actually we can say always that when we have an even function and it is multiplied by even function, we will get even function only, and we have even function and odd functions, we will get odd or odd into even, or we have odd and odd. So, again the minus minus will be positive. So, we have the even function. So, with this consideration what we see here, that f x is, if f is even, then we have even function. So, we have the integral value 2 over pi, and we can integrate simply 0 to pi f x cos n x dx if f is even, and if f is odd, then this will be odd function, and in that case this value will be 0 if f is odd. Similarly, for the coefficient b n, so what we have for b n, we have 1 over pi minus pi to pi and f x sin n x dx. This will be 0 if f is even function, because even into odd will be odd, and so if f is even, and this will give us 2 over pi 0 to pi f x sin n x dx if f is odd. So, in this case what we get if f is even function, we are getting a simplified Fourier series, and if f is even, then the Fourier series. So, for the even case, we have this b n 0. So, we will get only with the a's. So, a by 2 n 1 to infinity a n cos n x, and these a n with the simplified formula we can calculate 0 to pi f x cos n x dx and 0 1 2 and so on. And the second case, if f is odd, and this is also clear from here, this cos is even function. So, if f is even function, we will get only the combination of even functions on the right hand side. So, if f is odd, the a n's will be 0 and we will get only the sine series. So, we have the summation n from 1 to infinity b n and sine n x, and this b n will be given by 2 over pi 0 to pi f x and sine n x dx. So, now we consider example with this consideration. So, obtain the Fourier series to represent f x, which is given by x for 0 to pi and 2 pi minus x for pi to 2 pi, and then the function is periodic. So, f x plus 2 pi is f x. So, the Fourier series will be given by a naught by 2, and we have a standard period. So, n 1 to infinity a n cos n x plus b n sin n x, and we have for x 0 to 2 pi. So, if we look at the graph of this function from 0 to pi, we have this x and then 2 pi minus x. So, we have this, and again with this we continue with this period 2 pi. So, we have here 0, here pi, and then 2 pi and so on, here minus pi. So, this a naught we can get with the 1 over pi and 0 to 2 pi f x dx, 1 over pi 0 to pi, we have the function x plus pi to 2 pi, we do have 2 pi minus x dx, and the simple integration will give us just pi. A n is 1 over pi and 0 to 2 pi f x cos n x dx, and again we can break into the two intervals 0 to pi x cos n x dx plus pi to 2 pi and 2 pi minus x 2 pi minus x cos n x dx. And again I will skip these simple calculations, and we will get, in this case it is 0 when n is even, and we will get minus 4 over n square pi when n is odd. So, a we have calculated. Now, we go for the b n, and we no need to calculate b n because the function is the even function. So, we have even function f x is f minus x, and in this case b n will be 0 without going for any calculation. Sin n x dx, this will be 0, and therefore, we have this f x is equal to pi by 2 minus 4 over pi cos x plus cos 3x 3 square cos 5x 5 square and so on, and our x is from 0 to 2 pi. And note that we can write this equality because our function is continuous, and the function is continuous, then this average value is equal to f x. So, this series converges to the function value f x. Okay, so let us go for another example, and so determine the Fourier series of f x is equal to x square, and then find the value of the series and 1 to infinity minus 1 n plus 1 over n square and 1 to infinity 1 over n square. So, let us continue with this. First, the Fourier series of f x is equal to x square on minus pi to pi. So, in this interval we want to have the Fourier series of this f x is equal to x square. So, if we look at this function parabola, so we have this from minus pi to pi. In this interval we are interested to get this Fourier series expansion of x square. So, to get this we have to extend, or we have to put a continuation of this function to be periodic. So, we need to continue this as a periodic function and so on, and then we find the Fourier series, and that will be of course valid in this interval. So, since the function is an even function again, so clearly our b n will be 0 for all n, and now a n we can get. So, 1 over pi minus pi to pi, we have x square and cos n x dx, and that will be again 2 over pi and 0 to pi x square cos n x dx. This we can find out. So, 2 over pi, and we have here the x square and sin n x over n, the integral of this, limits minus, again this n will come, and we have 0 to pi, this 2x and sin n x dx. So, if we would pi or 0, this is going to be 0 anyway. So, we have 2 over pi and this minus 1 over n. Okay, so 2 over pi, and we take this 2 and this also outside. So, we have minus 2 over n, and then we integrate again. So, we have x and cos n x over n with minus sign. So, this is 0 to pi, and then we have with minus minus will be plus. So, 0 to pi, x is 1, and we have cos n x over n dx, and n should not be 0 and cannot be 0. So, for n is equal to 0, we have to calculate separately. So, we have minus 4 over n, and we have minus pi and minus 1 power n. So, minus pi and minus 1 over n divided by n, and put 0, it will be 0. So, we have again here 1 over n square, because after integral we will get 1 over n sin n x. So, sin n x will be 0 at 0 and also at pi. So, we end up with this 4 plus and this minus 1 over n, and over we get n square. Now we calculate a0. So a0 will be 1 over pi minus pi to pi x square dx, and this is just x cube over 3 and minus pi to pi, and then we have this 2 pi square over 3, because pi cube will come and that will be cancelled with this pi. So 2 pi square by 3. So now we can write in that form. So we have this a naught by 2, so pi square by 3 and plus only the cosine terms. So n 1 to infinity, we have this 4 minus 1 over n, our n square, and we have cos nx for x minus pi to pi, and again the function is continuous. So we can have this equality of this series to x square. And now the question was that how to find the series. So we have to get this minus 1 over n plus 1 over n square. So we are getting a similar series here. The only point is this cos nx. So if we put this x is equal to 0, we will get rid of this cos here. So let's first put, so this is series number 1. So if we substitute x is equal to 0, so left hand side we have 0, we have pi square over 3 plus n 1 to infinity, and x is 0, so cos 0 is 1, and we have 4 minus 1 n over n square, and this will, so we take to the other side this summation, and 1 minus we can accommodate here. So we get n 1 to infinity and minus 1 n plus 1 over n square, and this 4 will go to the right hand side. So we have pi square over 12. So we got the sum of this series. So the second question was, so if we substitute x is equal to pi in 1 again, so what we get, left hand side will get pi square, we have pi square over 3, we have plus n 1 to infinity 4 over n square, and we have minus 1 over 2 n, because cos pi will give minus 1 power n, and this is 1. So we get n 1 to infinity, and this 4 over n square, or 4 we can also take to the right hand side. So 1 over n square, summation n to infinity 1 over n square will be just pi square minus pi square over 3. So 2 pi square over 3, and then we have also this 4 there. So that will be pi square by 6 then. So this is the series of, so that's also one application of this Fourier series, where we can get the sum of the series. Now we go to the another topic of this Fourier series, that's the half range series. And this is just motivated by this sine or this even and odd functions. So, but in this case what we, so let me write this. Suppose that this f x is a function defined on 0 to L, and also we want to find the cosine or sine series of f x. So, f x is defined in some interval, and our aim is to have either cosine series or sine series of that function. So, what we can do this for this, so this can be done by extending f x to be an even or odd function. So, if we want to have the cosine series, we will extend that function as an even function, or we want to have the sine series of that function, we will extend this as a odd function. So, suppose f x is equal to x is given in an interval 0 to pi. So, if we want to have the cosine series of this, so what we will do, so we have this is the given function 0 to pi, f x is given is equal to x. Now, if we want to write this x in terms of the cosines, what we will do, we will extend this as an odd function, as an even function. So, this is, and then make it periodic. So, we have minus pi to pi, and we can make it then periodic. So, now this function is an even function. We can get the Fourier cosine series, and that will be of course valid for this f x is equal to x in this interval. And if you want to have the sine series of the same function, for example, if we want to have sine series, what we shall do, so this was the function given in 0 to pi, we can extend this as an odd function and then make this extension of this function. So, now we can write this function into sine series form, and that will be valid for this f x is equal to x in 0 to pi. So, let us just go for few examples in for this. So, obtain the half range sine series for f x is equal to E x defined in 0 to 1. So, we want to have sine series now. So, we need to go for the odd extension of this function. So, if this function is given here 0 to 1, we will get this odd extension of this function, and then we continue with this period minus 1 to 1, and we can then extend this as the as an periodic function, and also in that side. So, clearly in this case, since this is an odd extension of e power x in this 0 to x, that is the given function that we have extended. If you want to have the cosine series, we would have extended as an odd function. So, in this case, since this is the odd extension, this a n's will be 0, and b n we can get 2 over L 0 to L f x sine n pi x over L dx. So, in this case, now our period 2 L is 2 from minus 1 to n, that is the period. That means this L is 1. So, this b n is 2 over 1. So, 0 to 1 E x and sine n pi x dx. So, this we integrate and we get Bn 2n pi 1 minus e minus 1 over n over 1 plus n square pi square. So, now for this x between 0 and 1, this e power x we can represent by that Fourier series. So, 2 pi and n 1 to infinity, and we have this Bn. So, we have n and 1 minus e minus 1 over n over 1 plus n square pi square, and we have sin n pi x. Done. So, we now take an example where we expand f x is equal to x and x is given between 0 and 2 in a sine series and the same function as in cosine series. So, we take the first case, the sine series. That means we want to have the extension of this function 0 to 2 as an odd extension, and then we continue with this period as a periodic function. So, in this case a n will be 0 and this B n will be 2 over L 0 to L f x sin n pi x over L dx. So, 2 over 2, because our 2L has 4. So, L is 2. So, we have 2 over 2 0 to 2 f x is x, and we have sin n pi x over 2 dx. So, we integrate by parts. So, we have x and then this is cos n pi x over 2, and then we have this minus sign because this sign will give minus cos. So, minus 2 over n pi and 0 to 2, then we have minus 0 to 2 cos n pi x over L. The differentiation of x is 1, we have cos n pi x over L, and again minus 2 over n pi dx. So, this after simplification what we get minus 4 over n pi and cos n pi. So, if we then we get this Fourier series, this sine Fourier series 1 to infinity minus 4 over n pi cos n pi sin n pi x over 2, and x is between 0 to 2. So, when we write this x between 0 to 2, we can write this equality, and this is equal to x. This is nothing else, but this is given as x. So, this is 4 over pi. If we expand this just to see what kind of form we are getting. So, pi x over 2 minus this half and sine 2 pi x over 2, then plus 1 over 3, and we will here minus 1. So, this is plus anyway, and then we have sine 3 pi x over 2 and minus and so on. So, now we take the second case. So, we extend now function this f x as an even function, as an even function. So, in this case as discussed above, so we will extend this as an even function and then this extension to periodic function. So, we have minus 2 to 2 as an even function. In this case also our L is 2. So, now B n will be 0 and A n we can get in a similar fashion as we got there, 2 over L, so 2 over 2, 0 to 2 x cos n pi x over L 2 dx, and we integrate this to get 4 over n square pi square and cos n pi, that is minus 1 over n, minus 1 power n. So, for n not is equal to 0, and if we put n is equal, take n is equal to 0, we will get 0 to 2 and x dx, that means 2. So, in this case this f x will be, or x is equal to 1 plus n 1 to infinity 4 over n square pi square cos n pi minus 1 and cos n pi x over 2, or we can expand this, we will get cos pi x over 2 plus 1 over 3 square cos 3 pi x over 2 and 5 square cos 5 pi x over 2, and so on. So, now this is interesting to see that for the same function. So, we have taken this x function which was defined in 0 to 2 domain, and we get for the same function this cosine series, and that was that is given here, that is the cosine series. This is also x is equal to this in this domain x from 0 to 2, and we also have this sine series for this function which is also valid in this x 0 to 2. So, for the same function x, we have completely different expansion, one is in the cos, one another in the sine, and both will equally approximate this function in this domain. In fact, if we consider this series as a sum, so this sum is equal to x and this sum is also is equal to x for each x between 0 to 2. So, now we go to the last topic of this complex of this Fourier series, and that is the complex Fourier series or complex form of Fourier series. So, we consider f x a y 2, we start with the standard form. We can also continue with this Fourier series of function of period 2 L. So, a n cos n x plus b n and sin n x minus pi to pi, and with a n we have 1 over pi minus pi to pi, and this f x cos n x dx, and n is 0 1 2, and we have this b n 1 over pi minus pi to pi f x and sin n x dx, n is 1 2 3. So, what we know that this cos n x we can write with this Euler formula E I n x plus E minus I n x by 2, and this sin n x E I n x minus E minus I n x over 2 I. Now, we substitute this in this equation 1 for this cos n x and this sin n x term. So, what we will get, that f x is a naught over 2 n 1 to infinity, we get a n. For the cos, we have e I n x plus minus I n x over 2 plus this b n e I n x minus e minus I n x over 2 I. Then we have a naught by 2 n 1 to infinity and we take this for I n x from here and from there common. So, we have half also a n and minus this I we can multiply. So, we get minus I b n. So, if we take half a n minus I b n, and we will get E I n x plus similarly there a n plus I b n E minus I n x. So, we take it as we denote this by C naught, and this we denote it C n, a new constant. For this we denote it K n. Because the n is equal to 0, we will see in a minute that we will get C this a naught by 2. So, that is what here we name it C 0. So, with this notation what we have, the f x is C naught plus n 1 to infinity C n E I n x plus K n minus I n x. This is 2. Now, we also see what is the C n again, half a n minus I b n, and we substitute this a n and b n, 1 over pi was coming there. So, 2 pi and minus pi to 2 pi f x. Here we will get cos n x, here we will get sin n x. So, minus I sin n x dx, and this again we can write minus pi to pi f x minus I n x dx. So, we can see that the C 0 is just 1 over 2 pi minus pi to pi f x dx. So, that is a naught by 2, that is what we have written, and also this k n, if we take this k n, that is a n plus I b n. So, here plus will come and then we will have plus here. So, it is simply C minus n. So, then this equation 2 becomes that this f x, its Fourier series in this form, we have C 0 and 1 to infinity, and we have C n I n x plus C minus n minus I n x, or we can combine this and minus infinity to plus infinity, and we take the C n E I n x. So, this will automatically cover these terms as well as this term, and where our C n is our Fourier series in this complex form for this f x is and minus infinity to plus infinity C n E I n x, and this C n is 1 over 2 pi and minus pi to pi, and we have f x I n x dx, n is 0 plus minus 1 plus minus 2 and so on. So, this equation is called, or this form of the Fourier series is called Fourier series, and this is called the Fourier coefficients of that complex form. So, if we have a period for a function of period 2L, we have f x minus infinity to plus infinity C n I n pi x over L, and where C n will be 1 over 2 L minus L to L f x minus I n pi x over L dx. So, we quickly now go for one example of this Fourier series and the complex form. So, if we take a function f x e power x, and this x is between minus pi and pi, and then we have this periodicity. So, in this case we calculate the C n, that is 1 over 2 pi minus pi to pi our function n e minus I n x dx. So, we have 1 over 2 pi minus pi to pi e 1 minus I n x dx, and this we can integrate. So, we have e power 1 minus I n x over 1 minus I n, and we have the limits minus pi to pi. So, this just a bit simplification. So, we have 1 over 2 pi and 1 minus I n, and we will get e power pi minus 1 over n, because we will get e power n x, that is cos n x plus I sin n x. So, in that case this will give just minus 1 over keep 1 power n, and we have minus e minus pi and again minus 1 power n. Since this e power I n pi will be minus 1 over n, or we take plus or minus. In both the cases we will get cos n pi plus minus I sin n pi will be 0, and this cos n pi will give minus 1 power n. So, in this case and this again we can write this as so 1 over pi here 1 plus I n divided by 1 plus I n. So, 1 plus n square, and this sine hyperbolic pi, and we have minus 1 over n. So, this f x we have the sine hyperbolic pi over pi and n from minus infinity to plus infinity minus 1 over n, 1 plus I n over 1 plus n square and e I n x. So, this is the complex form of the Fourier series of a function, which is just equivalent to what we have seen the earlier form of the Fourier series. So, now I would say we had enough insights into the Fourier series with the help of several different kind of examples we have considered in this lecture. And in the next lecture we shall extend this idea of periodic functions to non-periodic function by extending their periods to infinity, and in that case this Fourier series will lead to the so called Fourier integral. And so, more on that in the next lecture, and thank you, goodbye.